In my humble and little calculus, I figure that's the furthest out. Our next speaker is going to talk about a technology that will harness a method of charging an electrical vehicle. Well, that's going to give new life to electric transportation. We know a little bit about this kind of technology. I alluded to it earlier in the day. You can now charge your cell phone by sticking it on a mat, which doesn't have wires connected necessarily. And the question is, can that be scaled up to deal with cars and highways? And the man to tell us about that is Braden Lim. How are you, Braden?
Great, how are you? Okay, so I'm Braden, and I'm here today because we have a couple concerns we need to discuss. But first, I want to do a little audience participation. So can I have everyone raise their hand who uses a horse-drawn carriage as their main form of personal transportation? Okay. Now can I have everyone raise their hand? This time, keep your hand raised if you use a personal vehicle, such as a car, truck, or SUV. Use that as your main form of personal transportation. Okay. Now keep your hand raised if this vehicle that you drive is an electric vehicle. Okay. Thank you for your participation. That's what I'm here to discuss today, is the transition from one type of personal transportation to another and the concerns we face in doing so. To start off, I just want to give you a brief history of what personal transportation has looked like. Throughout the 1800s, horse-drawn carriage was the main form of personal transportation. It was used throughout the United States, Canada, and the United Kingdom because it was the most economical and efficient means of travel at that time. It wasn't until the early 1900s that the internal combustion engine vehicle became a feasible option. Due to mass production of these vehicles, as well as new oil discoveries leading to decreased fuel prices, made these vehicles more affordable to the general public. So from the early 1900s to the mid-1950s, these vehicles went from being a luxury for the elite to a necessity for the everyday individual. And due to this rise in vehicles in the roadway, it created the need for new roadway infrastructure. In the United States, this was satisfied with the Federal Aid Highway Act of 1956. This act created 60,000 kilometers, or 40,000 miles, of interstate roadway in the United States. This made long-distance travel more feasible with your internal combustion engine vehicle. In total, this system cost about $500 billion in today's currency. So I want you to keep that figure in mind for some technologies I'm going to discuss later in this presentation. From this point forward, internal combustion engine vehicles have continued to dominate the transportation sector and still do today. But in the early 2000s, we saw a new interest in the electric vehicle. Initially, these vehicles were smaller vehicles that could only be used for short distance travel within one city. It wasn't until 2008 that we got the first highway-capable all-electric vehicle in the Tesla Roadster. This vehicle had an all-electric range greater than 300 kilometers or 200 miles, so it made longer distance travel more feasible. And it set the standard for what electric vehicles strive to be today with these larger battery capacities to travel farther. This new interest in electric vehicles came about for a couple of reasons. The first of which is the reduced environmental impact in the form of decreased tailpipe emissions. So if we look at a conventional vehicle right now, it generates about 300 grams of CO2 per kilometer driven. But if we replace that vehicle with an electric vehicle, this reduces to 154 grams of CO2 per kilometer, about a 50% savings. So as the transportation sector as a whole generates 15 to 20% of our global emissions, saving half or maybe even a quarter is a significant benefit overall. Second benefit to this technology is the reduced operational costs. If we once again compare these two vehicles, a conventional vehicle right now costs about 13 cents to drive per kilometer. And this takes into account the fuel to drive the vehicle as well as the maintenance averaged over the life of the vehicle. But if we replace this vehicle, once again with an electric vehicle, this reduces to 6 cents per kilometer. So while 7 cents per kilometer may not seem like a whole lot, the average driver travels about 21,000 kilometers or 13,000 miles every year. Saving 7 cents equals over $1,500 saved annually. But even with these environmental and economic benefits, these vehicles really aren't being adopted to replace internal combustion engine vehicles today due to some limitations. First of these limitations is range anxiety. As I mentioned, current electric vehicles have ranges of about 300 kilometers. Well, that's only about half of what internal combustion engine vehicles can drive. So if you want to travel long distances with electric vehicles, you have to stop about twice as often. In addition to that, you have to find charging locations. Finding charging stations for electric vehicles, they're far and few between compared to gasoline stations in the world today. And so you actually have to plan your routes to take into account where these locations are so you don't have to worry about running out of electricity. And once you get to one of these charging stations, you have long recharge times associated with electric vehicles. These vehicles can take hours to full recharge, compared to the minutes it takes to fill up with gasoline, making these vehicles not really ideal for longer distance travel. But if you're not traveling long distances, you may not run into these concerns, but you'll still have to deal with the large purchase price associated with electric vehicles. Due to the expensive battery components on board these vehicles that make up about a third of the purchase price, these vehicles are more expensive than conventional vehicles, leading to low adoption rates. And so with these limitations in place, it leads us to wonder what technologies are going to overcome these limitations such that we can move to electrified transportation in the future. And so one such technology is hybrid vehicles. Hybrids combine internal combustion engine components as well as electric vehicle components, so you have more energy efficient vehicles than conventional vehicles, but vehicles with longer ranges than electric vehicles. However, these vehicles are still really expensive because they have both components on board, leading to low adoption rates. Tesla is trying to address these concerns with longer range electric vehicles, as I mentioned. In addition to that, they've developed supercharger systems. And so these chargers can charge your Tesla from 0% state of charge to 80% state of charge in 40 minutes or 100% state of charge in 75 minutes. So while this is still longer than filling up with gasoline, it's significantly better than the hours it takes to fill up an electric vehicle currently. In addition, they've deployed a network of these superchargers across North America, Europe, and Asia, such that a Tesla driver can take their car from California to New York right now and not have to worry about where they're going to charge. This system is fantastic if you own a Tesla. If you own any other electric vehicle on the roadway today, this system is not compatible with it. And so as car manufacturers are developing new electric vehicles with longer ranges, we need a charging infrastructure in place that can be universal for all of these vehicles. Because hybrids aren't being adopted, and because there's not a high-speed stationary charging infrastructure in place, this has led to research in the area of in-motion charging of electric vehicles. One such concept uses overhead catenary cables similar to public transportation systems across the globe today. But how are you going to implement a system like this that works for both passenger cars and Class 8 trucks? You either have to have a very long mechanical arm on these passenger cars or have multiple different cable systems in place, making it not really feasible to satisfy all vehicles on the roadway. This has led to research in charging the vehicle from the roadway itself. So in this concept, you have an elevated conductive strip in the center of every lane and a mechanical system that lowers from the bottom of the vehicle. This overcomes the universality between these two vehicle types. But what are you going to do in places like Toronto, where it snows in the winter and the roads freeze over? It's going to lead to inefficiencies in this charging system, not making it feasible to introduce across the globe today. And so for these reasons, what I see as the technology that's going to overcome current electric vehicle limitations will look something like this. So you're probably thinking to yourself, that looks just like a vehicle driving down the roadway today. And that's the point. This is what in-motion charging using wireless power transfer will look like. It'll look just like a vehicle traveling down the roadway today. But to give you a better idea what's going on here, this technology uses a primary pad embedded under the roadway surface and a secondary pad mounted to the bottom of the vehicle. So as the vehicle approaches this pad in the roadway, communications is in place for the vehicle to tell the roadway when to turn on that pad as the vehicle is over it and turn off as the vehicle passes by. This system doesn't affect current vehicles on roadways, can be universally applied across all vehicle classes, and can be implemented across the globe because it works through rain, snow, and ice. The system can also be retrofitted onto current electric vehicles so they can use that technology as well. In addition to this, it directly addresses the limitations plaguing current electric vehicles. So if we revisit those, the first of these was range anxiety. Range anxiety comes from the fact that current electric vehicles have lower range than internal combustion engine vehicles. They have ranges of about 300 kilometers. But with in-motion charging in place, we can take that range from about 300 kilometers to limitless if we implement it on high-speed roadways where long-distance travel takes place, taking care of that first limitation. And because your vehicle will be charging from the roadway itself, you don't have to worry about finding charging locations, and you don't have to worry about the long recharging times associated with current electric vehicles, because you won't have to stop to recharge, taking care of these next two limitations. But what about that large purchase price? This technology still uses electric vehicles with expensive battery components on board. And so this is actually where in-motion charging comes back into play. Research that I have done evaluates consumer satisfaction of this technology and electric vehicles in general. Right now, about 70% of consumers can be satisfied using a 40-kilometer range electric vehicle, or about 25 miles, assuming that they charge at locations where they're stopped greater than 1 hour, such as home and work, where this charging infrastructure is usually in place. But if we implement in-motion charging only on higher speed roadways, this satisfaction increases from 70% to 99%. 99% of consumers can be satisfied if we implement this technology. And so they can use a 40-kilometer range electric vehicle, and so we can reduce the battery size from 300 kilometers to 40 kilometers, taking out a significant portion of those purchase prices associated with the battery, actually making electric vehicles cheaper than conventional vehicles on the roadway today, taking care of this final limitation. And so with any new electric vehicle technology, there's going to be large infrastructure costs associated with it. And this technology is no different. To implement this system on high-speed roadways in the United States today, it's going to cost about $1 trillion, or about double what the interstate system as a whole costs. But the difference between this technology and the interstate system is that it has direct savings associated with it, in terms of operational savings that I mentioned earlier, as well as savings with the purchase price of these electric vehicles. So if we can take some of those savings and put them back into these infrastructure costs, it actually leads to really reasonable payback times. So if we take a look at those payback times, this chart shows societal payback time in years on the y-axis and fleet penetration of wireless power transfer electric vehicles on the x-axis. So as conventional vehicles are replaced with wireless power transfer electric vehicles, there's going to be a greater savings associated with this technology to repay those large infrastructure costs. If we implement this technology on high-speed roadways in the United States today and replace a quarter of the vehicles with wireless power transfer electric vehicles, the payback time will be just over 10 years. And so 10 years is a really reasonable payback time for any new technology. So with the plethora of benefits that I've mentioned for both electric vehicles as well as in-motion charging and the feasible payback times associated with this technology, research is being done across the globe today to bring this technology to the masses. One such facility at Utah State University, where I'm from, it has a quarter-mile test track with this wireless power transfer infrastructure embedded in the roadway surface. It can be seen in the gray bars on the roadway itself. So we can actually put an electric vehicle on this track and drive it around as long as we want without having to recharge that vehicle with conventional means. Just proving that this technology can be taken to the masses today and that it is a feasible option forward to charge electric vehicles. And so this technology has the power to not only overcome current electric vehicle limitations, but actually make these vehicles more desirable than conventional vehicles on the roadway today because you have vehicles with longer ranges, so you can travel farther without stopping, and because these vehicles will be cheaper. Everyone wants a cheaper vehicle. And so my vision for the future and where this technology can take electric vehicles is that every person that raised their hand today when I asked how many of you own a personal vehicle will raise their hand in the future if I ask how many of you own a wireless power transfer electric vehicle. Can you imagine how powerful that would be? So as car manufacturers like Toyota have already stated that they're going to stop selling gasoline cars by 2050, this transition to electric vehicles is going to take place. As you saw with the audience participation earlier, this transition from horse-drawn carriage to conventional vehicle has already happened. There's even a select few in the audience today that have made the transition from conventional vehicle to electric vehicle. So with the benefits I've mentioned today, with reduced environmental impact, as well as reduced operational costs, and overcoming current electric vehicles, this technology can make the transition from conventional vehicles to electric vehicles more beneficial and more ideal than the transition was from horses to horsepower. Thank you.
So, Braden, do I understand that the technology that is buried in that pad, the charging pad, is commonplace, available today, easy to understand?
Yes, it's the same technology that you talked about with charging your cell phone currently. And
Right. And these pads don't have to be continuous. They're periodic, and you get a little zap as you go over them. Is that?
That's correct. You can either have little pads that can have zaps, as you talk about, or you can have longer pads that are continuous, so you can charge continuously. Or you can space these shorter pads close enough so that it's basically a continuous charge as well.
Now, I read in some of my research material that you priced this out at about $2.4 million a mile.
That's correct.
That's today's money, today's technology.
That's correct. That's to retrofit current roadways. So not actually build new roadways, but retrofit current lanes with this technology.
So 38,000 kilometers of highways in Canada. Do we have a quick mathematician who could do that calculation, please?
I don't know.
You're talking to governments, state authorities, local operators. What are you doing at Utah State to commercialize?
So the facility there, we're talking to all partners, so partners in the private sector as well as government, mainly government to implement this technology on a large scale because they own the roadways. A private company doesn't want to go in and put their technology in a roadway unless they're going to see some benefit. And so we're talking to the governments to bring this technology to the masses, but private companies are also interested. So
Do I see a startup in your future?
it's possible, but we'll see.
Thank you.
Thank
That was
you.
very persuasive.